Hey, hi everyone. Um, Good morning. So today we will continue the decision tree. This is day 10, and we'll continue the decision tree and then get more details on decision tree to understand it better. Um, so we'll refer to the uh, document that we're preparing. Okay, I should share the screen. Sorry. Oh yeah, I can enter here. Good. Let's get started. Let's look at the document. Okay, I think we took a sample. We tried to calculate information gain. Small correction on the information gain formula. The information gain formula is not this. It is missing the one of the key thing is information gain formula goes like this. Entropy of parent minus sum of weighted entropy of children. And 8 is under that 8. Okay, so there are a few things I found out. Actually, I've been looking at things, but I've not studied it. But few things I looked at is and on what we have learned with respect to decision trees are nothing what simpler that if the diagram that if you remember we are actually applying, we are dividing, we are like going with the principle divide and conquer. So what we are doing, we are using linear regression, and we are dividing the overall data set into smaller pieces and then conquering them separately. So what you do, if you remember the diagram that we have seen the other day, you split the overall data set basing on one feature with certain value, and break it when it becomes two parts. Those two parts, we try to classify them separately, so there are two smaller problems to solve, and then you it depends on whether your destination is to classify it into one particular class. It could be um, apple or orange, something like that. So once one of the child nodes reaches certain value, we stop there saying, okay, we've reached it. So we traverse the other node till we reach a conclusion. So, in order to take a call on which route node to be selected, which split is the right split to go with, to do that, we calculate same in linear regression for classification. We sorry, for logistic regression, for classification, we calculate error through uh, entropy, right? Same entropy is used here, and entropy of each, the root node, entropy of the child nodes, and basing on these all three, we calculate we calculate something called information gain, which is nothing but how much, which reflects um, how much the entropy is being reduced, because that's our objective, right? Even when we do logistic regression, and then if we do gradient descent or something like that, or linear regression with cost function and stuff, our objective is to reduce the overall loss as much as possible. So what we see, the entropy if we are at root node, and that's our solution, like one line is our solution, then what would be the entropy, right? So, and we try to reduce it. So uh, entropy of that parent node minus, if because of splitting it into these two parts, how much the entropy is reducing, we'll calculate it, and we'll pick up the best split, basing on which the entropy is reduced more, right? So if the uh, so information gain, when I say the are we also use the word impurity. Impurity is where for a selected list of values that are there, the more they are mixed up. So like the more they are having a combination of the both apples and oranges to something which has more specific apples, sorry, more specific oranges, that is pure. So we travel from impurity to purity, right? So we travel from x loss to reducing the loss as much as possible, kind of stuff. So that's what information gain is. So that's one way of calculating. There is also another way of calculating the the other way of making a decision on how which split is the best split to go with, and what is the feature, and what is the value that, like, so given overall data set, we can say x1 is equal to 1, x1 is equal to 0, or we can go with x2, we can go with x3. There are all combinations are possible, right? So actually I was spending more time on how do you pick up this feature, how do you pick up this value itself. That's the key thing, right? Because it's not easy. You have so many features. Let's say you have 1,000 features, and then there are, they might have continuous values, they might have categorical values, continuous values. Categorical values means where you can classify them, saying, okay, for example, somebody is not sick, we are trying to predict something, let's say, and we will say whether did he have seizures or not. So that's it. That's more like yes or no, right? Or it could also be like um, not a good one, but how many um, how many vomitings did he have, right? So let's be relative, like how many vomitings did he have in last 24 hours, something like that. Then we'll have a number, like it could be 1, 2, 3 or something like that. So the values, features, and values will be different. So the categorical will be where um, you have like whether he had fever or not, 0, 1. How many vomitings did he have? That is a continuous values. It could be two, it could be three, it could be any number. We don't know what the number is. So the number can be like regression series, right? Regression has continuous values, whereas classification problems have categorical values, where which can be indicated by classes. For example, apple and orange is one class, like class one, class zero, class one kind of stuff, right? Um, So, um, yeah, if for I, I think if it's a categorical feature, we are kind of good, right? So because what happens? You pick up either x1 is 0 or x1 is 1, and that gives you a split. So there are two values that you need to verify. You may be calculating the entropies. You may calculate the information gain and stuff, and you compare the information gain between x1 is equal to 1, x1 is equal to 0, and then you can make a call, right? uh, but whereas continuous values, how do you take a call? That's a big question, right? So um, there are so I think there are initially, I think what they did is they blindly went, picked up values, and then they did, for example, x1 is continuous values like 4, 7, 24, 20, something like that. Continuous values are there. They picked up each value, like x1 is equal to 4. Let's say if I draw a line with this value, and they calculated, it seems, for all possible values. That means if there are 1 million records, they calculated for 1 million records, which is like big calculation, right? That's like time taking a lot. For me, for some reason, that didn't look appropriate, because there's so many values. How do they? So I felt they would have come up with some optimization with it. Um, I find few optimization, but they're not that great. But the way they are, I'll tell you a few optimization that I've seen. So one optimization, instead of picking up each value, they take a mean of each values. Like there, if there is 4, 10, 20, 4 plus 10 by 2 is 7, so they go with 7. 10 plus 20 by 2 is 15, so they'll go with 15, like that. So instead of going with each value, they're reducing it almost like, you can say almost like half, right? uh, so matter of fact, not even half. Maybe if there are n fields, they may reduce it to n minus 1, that's all. So not a great optimization, right? Then another optimization is, they said, if you have a list of values and the corresponding classes, you sort the list of values, and then you pick up values where there is a transition. That is, let's say the output values are classes 1 and 0, and if you see list of ones and then become 0, then that you take a split point, so that our objective is to reduce the impurity. So what happens if you take that line, the top ones, whether it could be one or five ones, six ones, or whatever, assuming the output is 1 and 0, you take that as the left node and the remaining as the right node. So, but still, if you take a 1 million records, you don't know. The first one can be 1, second one can be 0. Let's say, assume that 101010 values are there for some reason. Worst case, most probably. Then you get split for almost same as the previous n minus 1 splits kind of stuff, right? So that is those are the findings that I had. I spent a lot of time on this to find more optimizations, but um, I couldn't find more. But I think the objective is, through which the people are thinking is, categorical features are the best ones that we can use. So how can we convert the continuous values to categorical values? Maybe classify it into categories basing on the range. Like, you take something where the values are ranging from 0 to 10. Maybe they will, if they want to classify as two values basing on I mean, maybe they want to classify similar to the output, and they might classify them as 0 to 3, 3 to 4 to 6, and 7 to 10, possible. And the three classes are 0 to 5, 5 to 10, right? Um, I That's that could be an optimization technique, but the accuracy of it, or is it the right thing to do, may not be, because um, maybe ones and zeros are majorly in 0 to 5, and you are labeling all of 0 to 5, you're making it categorical, and then you're putting 0 to 5, and it might not be an optimal split for you, right? So even if we do, we need to repeat it. You can't just at root node level, let's say you go with 0 to 5 and 5 to 10. um, After splitting it into two values, again you need to pick up all the values and you need to split it. Like 0 to 5 should be further split, and then 5 to 10 should be further split. I mean, this is my thinking of what one optimization that could be done to convert continuous values to categorical values. Uh, the mathematical calculation of this, does it help? And with respect to accuracy of the decision trees, with respect to doing it each value based, is there any difference? I feel there might be a little difference, but I don't want to get into those details. It will take more time, but I'm sure there could be a lot of optimization that we can think of, right? Another way of calculating this, the overall decision making of the split, is on information gain. There is also another one they use called Gini index. Gini index is 1 minus sum of uh, probability at I square. So this is easy. For a given node, they calculate probabilities of each um, value, and they square it, and then they add it. Uh, when I say square of probability of each value, I mean to say um, not each value as in x1's value or x2 value or something like that. They calculate probability of each output. So the focus is always on output, not influenced much on the input kind. That's just because our objective is to find out the output, right? So what we do, Gini index, you calculate the Gini index of the root node, and then you calculate. I have an example that I asked ChatGPT. I can show you guys. It is nice actually. It gives you a good understanding. I just asked take two or three features and try to build a tree using Gini index kind of stuff. So it has picked up features. Feature one, it has taken more categorical, so the calculations are easy. But for us also it is easy to understand. Let's assume the feature one is these values, feature two is these values, and target is these values. Then the approach is to calculate the gene index for root node. Root node has all the values as is, it's not split. And then when you split it basing on certain feature, the possibility is feature 1 is equal to 1, feature 1 is equal to 0, feature 2 is equal to 1, feature 2 is equal to 0. There are four possible ways in which you can split it. When you split it basing on each of them, the target is split in different ways. So you calculate the gene index for each four of them, and see how they impact and what's the right split to do. So for root node, the math is four, there are four ones out of eight, so it's 1 minus 4 by 8 whole square plus 4 by 8 whole square. So one probability of 1, probability of 0 whole squares, right? 1 minus probability of 0 whole square, probability of 1 whole square is equal to 0.5. That is root node. Now to select a split on which split is good, feature 1 equal to 1. So that means here, if you pick up feature 1 is equal to 1, it is here 1 1 1 0. So three ones and zero on one side, three zeros and one on the one side, right? So feature one equal to one. Uh, equal to one, you get class zero two times out of three. Um, let's look at this. So split on feature one equal to one. Let's look at that. So if I say feature one equal to one, feature one equal to one, then for me, what happens is on the one side you'll have uh, three ones and one zero, and the right side you'll have three zeros and one one. Correct? The probability for both are actually same divisions. The probability will be similar for both of them. So this will become technically it should become. Why did he split the whole 10 into 3 and feature is equal to 1? Feature is equal to 1 is again 1, 2, 3, 4. Something wrong with this calculation is what I'm thinking. Okay, let's see. So it will become 3 by 4 and 1 by 4. It should be like this, 3 by 4, 1 by 4 for each node. One, and then for each node you're supposed to have, you should have supposed to have two nodes. So 1 equal to 0 is 3 and 5 split. 4 0. Okay. Feature 2 is 2 and 6 split. And here also if you see, okay, recalculate the splits is supposed to be feature 1 and feature 2. If you look at it, 1 0 1 1 0, that is 2 2. This is okay. 1 and 2 2 means 2 2 only. Feature 2. Subset 1 is 1 1 1, subset 2 is 0 0 0. Now this guy is doing definitely wrong. Feature 2 see the it's wrong because it's supposed to be 4. I mean, sum of the subsets should be 8. Correct? How is feature 2 is equal to 0? Only 3 values on the left side and 3 values on the right side. How is that possible? And what happens to the remaining 2 values as if they're unknown? So Okay, chat GPT is going wrong here, but um, but if we do on our own, what happens if feature 1 equal to 1, if we take it, then what would happen is it'll split it into 3 comma 1 sets, where 3 ones and 1 0, 3 zeros and 1 1. So it'll be 3 by 4, 1 by 4. So it's 1 minus 3 by 4, 1 by 4 whole square. So it is 1 minus after 10 by 16, 5 by 8, 8 6, 48, 0. Point 22, 16, 45, 0.625. 1 minus 0.625, and then that will become 75, 375, 0.375. So here, if f1 is equal to 1 is one line, 0.375 is the gene index. F1 is equal to 0, the split would be f1 is equal to 0, then the split would be 0, 0, and 1, 0. Similarly, for obviously, if it's same thing, I think it's gonna be f1 is equal to 0 is also going to be 0.375, and f2 is equal to 1 will be I think uh, two zeros and two ones is what we have seen, right? 0 1 1 0. Yeah, so it's two zeros and two ones, two zeros, two ones. So here also it will be the same, but 2 by 2 is 2 by 4 whole square plus 2 by 4 whole square is, that is 1 by 2 whole square. 1 by 4 plus 1 by 4 is 1 by 2. 1 minus 1 2 is 0 point. Wherever there's equal purity, it will become 0.5, as is similar to our root node kind of stuff. So comparing these two, I think we have the least Gini index is achieved with either f1 equal to 1 or f1 equal to 0, and you can pick any one of them and move forward. That will be the scenario. Let's say we pick up f1 equal to 1 as our root node, then uh, you have two splits. One is 3 ones and 1 0. Another one is 3 zeros and 1 1. Now again, we can for each node we should separately take it and then think of uh, splits. We f1 is already classified, so we can't take f1. F1 will be singular, so we, we should go with f2, and so we should calculate for f2 is equal to 0 and f2 equal to 1 for each of them. Uh, Equal to 1 for each of them. So let's look at this is little tricky because yeah, but we'll take it. Feature one on the left side. Feature one is 1, right? That's already the root node. So it'll, like, let's pick 1 1 1 1. Then feature 2 corresponding values needs to be picked up. It's 0 1 0 1 1, 1 0 again, and 1 1, and corresponding target values are 1 1 and 1 and 0, right? Coming to the other side of it is 0 0 0 0, feature 1, and corresponding values are feature 2 is 1, um, 0. I think all rest of them are zeros. Oh no, 1 0. Yeah, it's equivalent split in feature 2, and the target values for this will be 0 1 is 0, 0 0 is 0, 0 1 is 1, 0 0 is 0. Okay, that's a good. Um, Now on each of them we should pick up feature 2 is equal to 0 and feature 2 is equal to 1. If feature 2 is equal to 0, we get feature 2 equal to 0 and feature 2 equal to 1. Both should be calculated. Feature 2 is equal to 0 is a split. You get 1 comma 1 on one side, 1 comma 0 on one side. Feature 2 is equal to 1. If you pick it up, you get 1 comma 0 on one side and 1 comma 1 on one side. This is for the left node. Coming to the right node, if you pick up feature 2 is equal to 0, um, equal to 0, you get 0 0 on one side, 0 1 on one side, and feature 2 equal to 1 on the right node, it will become 0 1 on left node and 0 0 on the right node. So looking at this thing, we are getting few leaf nodes. Once you get leaf node, what would happen is, I think, um, 1 minus, okay, anyways, let's just do it. Gini index, right? 1 minus 1 by 2 whole square, no, sorry, uh, plus 0 by 2 whole square, 2 by 2 whole square plus 0 by 2 whole square. If 1 comma, for 1 comma 1, if we calculate, it's 1 minus 1 is, this is 0. So Gini index is 0 for the most, it is it is 0.5 for the most impure and 0 for the most pure. It is 1 comma 1 has 0, 0 comma 1 will have 0. uh, Here it is 1 comma 1 is also 0. So if you we can 1 comma 0 will be 1 by 2 1 by 2, that will be 0.5, and we have 0 comma 1, that's also 0.5, 0 0 0.5. So obviously we should, both are of same, so you can take any one of them here. Let's say you pick up f2 equal to 1, because we picked up f1 equal to 1. Let's pick up f2 equal to 1 for both sides. Then it will split it as 1 comma 0 and 1 comma 1, and here it is 0 comma 0 and 0 comma 1, same, 0 comma 0 and 0 comma 1. Leaf nodes need not be split because they're already on the last mile, and then 1 comma 0 and stuff now. Oh, interesting. 1 comma 0 and 0 comma 1 that are there with us, that is, let me mark them here. uh, we're picking feature 2 is equal to 1, right? And these two, and here it is feature 2 equal to my bad, feature 2 equal to 1 is actually making a good split here on the left side. It makes 1 comma 1 on one side, feature 2 equal to 1, and the remaining 3 zeros on the other side. Maybe I've written it wrong way. Doesn't matter. So you get further splits there, and I think 1 comma 0 once you have here. Um, oh, okay. So not always basing on. This is interesting, right? What happened? So x1 is 1, x2 is 1, and output is 1. X1 is 1, x2 is 1, output is 0. This two combination is there. Then you get 1 comma 0 on the one of the last node. You already have exhausted x1 equal to 1 and x2 is equal to, and if you go with x1 equal to 1 or x2 equal to 1, both combination, you see that the input values are 1 1 1 1 1 1 0. You can't split it further, right? Because the only possibility is x1 equal to 1 and x2 equal to 1, and both of them will give you same leaf node. It can't be split further. So uh, the final leaf nodes can't always take full purity. That's a good learning. So you might also end up in a set which can't be split further into two pieces. Ah, interesting. Good learning. Nice. So that's how this example goes, basing on Gini index kind of stuff. This is there are two parts. When to use which one? If you have more categorical, you go for Gini index. If you have more continuous values, you go for information gain. And For the same example that we picked up, if we go with information gain, what happens is the information gain will give you a solution which is more overfitting um, than Gini index. Um, I use the term overfitting. That means it overfitting and underfitting is nothing but overfitting is you assume that the values that we see itself is the universal values, and then um, your algorithm is more biased towards those values. So what happens when you get a new record, and for some reason if the new record is outside the scope of the training data, then that will predict wrong, because you are assuming that whatever you have is the universal set. There's nothing more outside it. So you overfit to that particular set that is given to you. So overfitting will reduce your probability of predicting the unknowns properly. Underfitting is where you don't you even if you give a value that is there within the trained data set, it do not predict properly. So the unknown, maybe it will predict properly, but predict it may or may not. But for even the training data set, if you repeat it also, it will not predict properly. Objective is to go in between, where it should not predict correct values for all the training data sets. So that's a tricky piece part of it. So that means tomorrow when you get a training data sets value, uh, it, it it should not 100% predict a right value for all of the values. That is how we can actually um, that is how you can actually predict, saying there is the unknowns, right? Because the unknowns are different values from this, and if this is overfitting to this, then you don't predict properly on the unknown values kind of stuff. So that's with the decision tree. I thought I'll cover a little bit on random forests. Is write code for one of them to. So let me complete it. Like, let me take 5 more minutes and quickly complete it. Random forest is nothing. That's just ask. What are random forests, and why do we need it? It's an ensemble learning technique. Okay, I'll say what is ensemble learning technique. Ensemble is nothing but so decision trees is more divide and conquer is what our learning was, right? Where we divide the data sets by using a model at one level. Like you use one linear regression or logistic regression at one place, using which you split it in two parts. Again, you use another model. So if you look at it, if you say that this one algorithm, and even if it's one line, if you call it one algorithm, right? So what you did, one line and childs, and then you used other lines, one other algorithms, and different ones, and then you keep splitting. You use multiple. So you use multiple models together, and together these models actually has given you a specific output. So ensemble learning technique is where you do the same thing by using different models, and the models can also, here what we did, we were using logistic regression for decision tree classifier. There is also decision tree regressor also, which helps us in predicting a value, where you split it, and then, yeah, obviously you can't predict, because the output data set is regression, is continuous value, so you can't predict an unknown value. But what we do is the known values will be taken, and you if you have split to certain level in decision tree regression, we take an average of those leaf nodes or something like that, and we move, and we'll put that as prediction. So my take would be decision tree for classification is looks much appropriate than regression, but it is possible to have regression. But coming back to random forest, you can actually pick up multiple models. It could be, and from ensembling techniques, it could also be different models. For example, you take, but it should be similar. You can't take one linear and one logistic. Doesn't make sense, because your prediction, your model that you pick is trying to predict the same thing, right? Like, one can't be classification, other can't be regression. So um, it doesn't make sense. But for example, you can take logistic regression and decision tree. Possible. Logistic regression is one algorithm. Decision tree is uh, multiple logistic regressions put together again. Similarly, decision tree and itself is combination. Random forest is again ensemble learning technique used for classification regression. In sense, a collection of instead of going with one single decision tree, you can go with a collection of decision trees, and we calculate the output of uh, these decision trees, and basing on the output of all the decision trees. For example, let's say if you take 10 decision trees, and six are output of these decision trees is six of these decision trees says for a given unknown values, it classifies them as apples, four of them as oranges. We take go with whatever is classified more. Six is higher than four, so you go with apples. If there is five, you pick any one, or so you pick up the majority kind of stuff out of this. So it's as simple as that. There is nothing very complicated about random forest with respect to same decision trees, but you use random decision trees. But as I said, the complaint on decision tree for me is uh, the math is pretty um, hard to calculate, right? So where you have 1,000 features, and then you have 1 million records, so you need to repeat your calculation basing on the splits and stuff. You need to do a lot of 1 million, uh, 1 million output points on the root node. You split them. Again, you need to go to 1,000 features. All 1,000 features you need to calculate before taking a call what should be on the root node, and again you need to repeat the same thing for the below. So this is definitely a huge exercise. Considering that fact, how do can we optimize it is one way. Especially if you take all 1,000 features and all million records, you might end up in overfitting the particular decision tree. So one of the technique is to not go with all 1,000 features. Instead, in when you go for random forest, you pick a subset of features and subset of values. For example, out of the 1,000 features, you can say I pick up 50 features and then build one tree. And then instead of 1 million records, I'll take a subset of um, mm, let's say 1,000 values, right? And then you build on top of it, and using those subsets. So if you take 100 features out of 1,000, you can split it into 10 set of features, right? So 10 set of features, and you correspondingly randomly sample records from the 1 million records, and you train on top of it, right? The the lower the i mean the lower the sample set, the less accurate the predictions will be. So, and the lower the features, the less accurate the predictions would be. But what we're doing, you're using an ensemble learning technique. So um, we are we are taking a subset of the features and subset of values, and then we are conquering them, each of them separately, and then we are looking at the aggregated view of it. So um, this is giving, as it says, why go for higher accuracy, robustness to overfitting, feature importance. And we sample the features and then look at it. um, mm, we are not splitting, we are sampling the features. So we might also have repetition of features in a few of the trees, which is also possible. Handling of missing data and outliers, it seems, I don't know how it handles are robust to missing data and outliers. They can handle data sets with missing values without the need of imputation, and outliers have less impact on the overall performance due to the ensemble nature of the model. Okay. Yeah, parallel training, which is good, because you even in decision trees, right? You split, once you split it, these two becomes independent. You can test both of them. You can work on both of those trees separately. Then it becomes four, like one, two, two to four, and all that. Let's say if it becomes, if they're assuming you don't find a leaf node, then four can also be parallel executed. So similarly, random forest, if there are 10 decision trees that you pick up as random forest, then 10 of them can be parallelly uh, versatility. Random forest can be applied for both classification and inheritance, making them versatile for a wide range of supervised learning problems. Okay. Our animals are powerful and flexible. Okay, let's ask last question before we close it. What are different variants of random forests with different optimizations? Provide a tabular list with a brief on each of them. Yes, random forest, extra trees. There are a lot of variants on random forest, because different people would have come and they would have um, given different variations of it on how to pick up. Because once you say random forest, you're picking multiple decision trees. So there are a lot of questions, right? How do we pick up this? How many multiple trees can we pick up? What is the um, um, how does the decision making overall happen, right? That's the key thing on mm, number of, how do you split into number of trees, how do you make the choice of features, how do you make the choice of number of values basing on that, and then optimizing it further. But splits are chosen randomly without optimization. Decision trees and extra trees, totally random decision trees, random splits with no optimization. Isolation forest, an anomaly detection method based on random forest that isolates anomalies in the data. Okay. Rotation forest, random forest where each decision tree is trained on a random subspace of the um, feature space. Okay. Extremely random, a variant random. Yes, randomness in feature selection, streaming randomness, updating models incrementally. Yeah. So, XGB, extreme gradient boosting and gradient boosting machine are both ensemble learning techniques that be family of gradient boosting algorithms. Well, they also have distinct characteristics. XG boost is optimized for speed and efficiency. It implements other guardrails such as parallelism, tree pruning, cache awareness. Whereas GBM is not an optimized as XG used, and may be slower, especially when dealing with large data sets. XG boost includes regularization techniques. XGBM does not have built-in regularization techniques. Use Oh, so I was actually thinking XGB is always extreme variant boost is only applied for random forest. It can be applied for any algorithm, is it? Good learning. Random missing value XGB has been some random as parallelism does not support parallelization. Your performance. So XGB and GB are they applied only for random forest or different? Limits are not specific to random forest, they are both gradient boosting. Okay. To various types of models, including decision trees, linear models, and other types of decision trees, linear models, other base models, various tasks to upload various machine learning tasks, including classification, regression, ranking, so XGB and GB are not specific to random forest and then can be applied for anything. Buddy. Ow. I missed on this logic. I was thinking that XGB and GBM are specific to random forest. Good point. And I applied them also without knowing this. Yeah. But this um, extreme gradient uh, boosting and gradient boosting all machines are actually widely used techniques. Obviously, XGB sounds much better than GBM, so people don't use GBM. They go for XGB, XG Boost, and XG Boost is widely used in CAG problem solving in Kaggle and stuff. Which um, for me, that was actually a winner for my Kaggle competition kind of stuff. So it's a good one. But again, we need not rely on as we understood about ensemble learning techniques. So we need not rely on specific models. Also, you can actually pick up multiple models, and you can apply this XE booster on top of it as well, and the ensemble model, and that's also um, more accurate. That also gives more accurate than following going with individual models kind of stuff. So these two are specific techniques. So that's it for today. I think we have crossed time. So nice. We've completed decision trees, random forest. We looked at what is different kind of random forests that are possible, and we also used what kind of optimizations or approaches that we can use with respect to XGBM, GPM, and stuff. Um, that's it. So we'll move on to the next topic tomorrow. I'll decide on the next topic and let you guys know tomorrow when we get started. Okay. Thank you.